All right, now we have found a method for computing eigenvalues, eigenvectors, but it was quite complicated. Let's find a simpler way. Okay, so remember, let's start with a definition of eigenvector, eigenvalue. Eigenvalue is a number such that there's a vector x that satisfies ax equals lambda x. Let's rearrange this. X minus, I can write this as ax minus lambda inx. We've done this before. Inx is the same as x. We've just moved it to the other side. And we can write this as lambda minus inx equal to 0. So what we have here is a matrix times the vector is equal to 0. Actually, x is in the null space of this matrix. X is in the null space of this matrix. Now, we know that this matrix may not always have a null space. If this matrix has a null space, we can find x and we get an eigenvector. How can we guarantee that this matrix has a null space? Well, that's going to have a null space if this matrix is singular. How can we guarantee that this matrix is singular? Well, in the last section, we found out that a matrix is singular if and only if it has 0 determinant. Okay, so there's where determinants come in. If we can choose lambda to make this have 0 determinant, then we can find an eigenvector by solving for the null space of that matrix. Okay, so that's the strategy. We're going to find a constant lambda such that a minus lambda I has determinant 0, and then since that's singular, it has a null space, we can solve the null space for the eigenvector. Okay, all right, so let's go. If A is a square matrix of size n, then the characteristic polynomial is defined as the determinant of A minus xin. All right, now, why do we call this a polynomial? Because as we'll see when you work this out, that if you do compute this determinant, it's going to be a polynomial in x, and we'll see that in the examples following. And remember that determinant is a number, so that this is going to give me a number that depends on x. It's actually a polynomial in x. All right, so let's look at an example. If you compute the characteristic polynomial of this matrix, okay, so I'm sorry, we want the characteristic polynomial of this matrix, so we want the determinant of this matrix minus x times the identity. Okay, so we're going to have to do this using algebra. We can't do it just with numbers. Remember how you do this. You do the row expansion. We're going to expand on the first row. So I'll take this number times the first matrix. That's this submatrix here. Okay, then when you finish that, and then the next time it's going to be times minus 8 times, this is going to be minus 1 to the 1 plus 2 times the determinant of the submatrix, which is obtained by crossing out the rows in the column. So that's 12, 4, 24, 7 minus x. Okay, and this is going to be plus minus 4, and then that's first row, third column, so that's going to be a plus. Okay, and then we have cross out the last row, last column. So we take this minus 4 and multiply by that matrix. Okay, and then we can do these 2 by 2 submatrices. Notice that here we're going to have, here's a factor of x, some other factors of x. It turns out we have a polynomial that has degree 3. And that's always going to be the case. You can't have degrees of x higher than 3 if you have a 3 by 3 matrix. If I have a 5 by 5 matrix, I'd get up to x to the 5th. All right, so here's my characteristic polynomial, and it turns out to factor. You can factor using Wolfram Alpha or some other software, or Sage. Okay. Now, this gives me my candidates for lambda. So the two roots are lambda equals 3 and lambda equals minus 1. These are going to be my eigenvalues. Okay, so once I have my eigenvalues, I can plug in, take A minus eigenvalue times identity, find the null space, and that's going to give me my eigenvector. Okay, so let's summarize this. Lambda is an eigenvalue of A. That means that there's a non-zero x such that ax equals lambda x, which is the same thing as saying there's we can solve this equation just pulling lambda x to the other side, which is the same thing as saying that ax minus lambda in x equals 0, because the identity times x is just x, which means that we have the matrix A minus lambda in times x is equal to 0. We just used the distributive law, and that only happens when A minus lambda in is singular. And that only happens when the determinant is 0, and that only happens when the characteristic polynomial evaluated at the number lambda is equal to 0. Okay? So the example that we just did, when we computed the characteristic polynomial, it factored like this. So my two eigenvalues are 3 and minus 1. Okay. Now, we talked about eigenvectors, and we mentioned that the set of eigenvectors for a particular eigenvalue is closed under scalar multiplication, and it's also closed under addition. Now, we're going to formalize that definition now and talk about the eigenspace. I mentioned that a couple videos ago. So let's take this definition. Suppose A is a square matrix and lambda is an eigenvalue of A. Okay? Then the eigenspace for A is the set of all eigenvectors of A for the eigenvalue lambda together with the zero vector. Okay. All right, now, so let's prove that in fact the eigenspace for a particular lambda is a subspace. That's what this theorem says. Suppose A is a square matrix of size n and lambda is an eigenvalue, then the eigenspace of matrix A corresponding to eigenvalue lambda is a subspace. First, we have to show three things. We need to show the zero vectors there. We need to show that the eigenspace is closed under addition and closed under scalar multiplication. We actually did these two things before, but it doesn't hurt to see it again. Now, the zero vector is in the eigenspace by definition because we've added that in. And then here we're just using the additivity, the distributivity of matrix multiplication to show that if I take A times two eigenvectors, the sum of two eigenvectors, then it will satisfy the same eigenvalue relation. Similarly, if I take A times scalar multiple of an eigenvector, it will satisfy the same eigenvalue relation. Okay, and here we're just restating what I mentioned before, is that once you find an eigenvalue, then you just want to solve A minus lambda in times x is equal to 0. That's exactly the same thing as a null space. So the eigenspace for matrix A associated with eigenvalue lambda is exactly the null space of this matrix A minus lambda in. Okay? And this is just going through the steps that we mentioned already. All right. So let's see if we can find the eigenspace for this matrix. Okay? When we did this matrix, we showed that there were two eigenvalues, 3 and minus 1. So to find the eigenspace for lambda equals 3, I just need to take that matrix F, subtract 3 times the identity, so I need to subtract 3 from each of the diagonal elements, row reduce, and find a null space. Okay, and this is what we've done before. You row reduce, here you have free variable, 2 pivots. You can set your free variable equal to 1, and then you get the other 2 variables. So here's my null space. That's going to be my eigenspace corresponding to eigenvalue 3 for the matrix A. Okay, now for lambda equals minus 1, we have to subtract minus 1 times the identity. That's the same thing as adding the identity matrix to F. So we added 1 to each of the diagonal entries. So minus 13 plus 1 is minus 12, minus 7 plus 1 is 8, 7 plus 1 is 8, and the rest of the entries stay the same. By row reduce, I get this. I have 2 free variables, which I can choose arbitrarily. So I have a null space that has 2 dimensions, and these are both eigenvectors of the matrix corresponding to eigenvalue minus 1. Okay, so this is a standard computation that you should get very good at because it's one of the really boilerplate computations that are used in mathematics. All right, that's it.